Greetings to you as we take on 4.4 transformations of functions. And basically what we're looking at here is answer to questions like this. Hey, here's a typical function. F of x equal x squared. A parabola, right? Yeah, but what if I wanted this parabola to be, say, several units to the left? I would be transforming it. I would be moving it, what we call a horizontal shift. We're going to be looking at horizontal shifts. Hey, here's another typical function. This is the absolute value function. What if I wanted to move this whole function up or down? That would be something we call a vertical shift. And we're going to be looking at that as well. Hey, here's another function. F of x equal x squared. What if I wanted to, in fact, flip this function across the x-axis? Make a mirror image of this guy across the x-axis. That's another kind of transformation called a reflection. You can either reflect across the x-axis or you can reflect across the y-axis. Hey, here's another familiar guy, same guy, the parabola. What if I wanted to thin this guy up? He looks a little porky here. Looks like he's been eating a lot of ding-dongs and so forth. What if I wanted to thin him up a bit, make him look like this? This is another kind of transformation known as either stretching or compressing. So we will be doing all these kinds of transformations and looking at the results of what happens to these ordinary functions when we transform them in a particular way. Now, one thing you're going to need to have handy is your basic function sheet. This is in one set of your notes, the last set of notes, other types of functions. Run at least this page off. This has the first 6. This is the last 3. So that you can have this handy, because you're going to want to refer to this because these are the basic functions that we're going to be transforming. All right, so have this guy handy. I will also be putting this little worksheet on your Quickly content available. It shows what happens when I do these transformations of functions. For instance, here's the common parabola, f of x equal x squared. What if I wanted a new function that was moved to the left 4 units? Look what happens. Inside the value itself, the thing that's being done, I'm squaring something. Inside the thing I'm squaring, I add 4. You go adding, wouldn't that move it to the right? No, it's just exactly the opposite of what you would think. Adding 4 moves a function to the left. Subtracting 4 in the parentheses moves the function to the right. So here's the first transformation known as a horizontal shift. I can also move a function up or down. Let's use the same function, the parabola, f of x equal x squared. What if I wanted to move the whole thing down, let's say 3 units? Well, this is easy. Down 3 sounds like minus 3. That's exactly what I do. At the end of the function, you either add something to make it go up, subtract something to make it go down. Vertical shift. And I can do them both. I can have a vertical shift and a horizontal shift in the same transformation. Here's a typical function, the absolute value function, f of x equal absolute value of x. I can move it 4 units to the left by adding 4 inside the value itself, inside the operation, which is absolute value. And I can move it down 2 by subtracting 2. This should not seem too unfamiliar to you. Remember the vertex form of the parabola? This is the vertex form of the absolute value. The opposite of this number, -4, and exactly this number, -2, becomes the new vertex of my transformed function. What do I do to reflect something over the x-axis? Here's a familiar function, f of x equal the square root of x. If I wanted to flip it over the x-axis, I would simply put a negative in front of it. So a negative in front of the whole function flips it over the x-axis. Reminds me, earlier I said this is f of x equal x squared. Sorry, that's f of x equal x squared. This is f of x equal the square root of x. So if I want to flip it over the x-axis, just put a negative in front of the whole thing. What if I wanted to flip it across the y-axis? That's when I put the negative in the operation itself, in the square root, in the absolute value, in the thing that's being squared. So if I want to flip this over the y-axis, I make sure my negative is within the operation. Over the x-axis, it's on the outside. All right, those are the reflections that we're going to be, the transformations that we're going to be looking at. And I will make sure this sheet right here is available to you. We did get to stretching and compressing, right? Here's my ordinary common function, x squared. What if I wanted to thin it up, what we call stretching? I simply multiply the whole thing by a number greater than 1. So if I multiply x squared by 2, 3, 7.5, 100, it's going to thin the thing up, what we call stretching it. That's if the number in front of the function itself is greater than 1. Well, what happens if I multiply the number, or if I multiply the function by some number in between 0 and 1? Something you could think of as a fraction less than 1, or a decimal less than 1. Something like 0.5, 2/3, 3/7, something that's in between 0 and 1. That flattens the thing out, what we call compressing the function. So to multiply it by a number greater than 1 thins it up. To multiply by a number between 0 and 1 flattens it out, compresses it. All right. This sheet is going to be in your notes, and this is important. If a function has been transformed from a simpler function evaluated in this order, there is an order for evaluating what's been done to a function. First of all, see if it has been moved left or right, horizontal shift. Secondly, see if it's been multiplied by a number between 0 and 1 or greater than 1, stretching or compressing. Thirdly, see if there has been any reflection. Has the whole thing been made negative? That would flip it over the x-axis. Has the inside the operation been made negative? That would flip it over the y-axis. And finally, after everything else is done, see if it's been moved up or down, a vertical shift. All right. In this section, you and I have two concepts to consider in talking about our functions. Is a function an even function, or is it an odd function? Even function answers this question. Does f of negative x equal f of x for every x in the domain? That's kind of vague, and I would expect it to be vague. So use a specific number. Does f of negative 2 equal f of 2 for every x in the domain? Does f of negative 5 equal f of 5 for every x in the domain? If I get a yes, then I call this thing an even function. Here's an example. F of x equal x squared is an even function. Why? Because f of negative 3 and f of 3 are exactly the same thing. Hey, square negative 3, get 9. Square positive 3, I get 9. So f of 3 equals f of negative 3. Even function. Well, what if when I put in 3 and negative 3, I got the opposites instead of the same thing? That's what we call an odd function. Does f of, let's say negative 2, does f of negative 2 equal the opposite of f of 2 in a particular function? If I get yes for that, that's what we call an odd function. Again, talking about x's and negative x's is rather vague, so use specific numbers. Does f of negative 2 equal the opposite of f of 2? I don't know, let's see. F of negative 2, this is the cube function. Negative 2 cubed is negative 8. F of 2, 2 cubed is positive 8. So what I find out is that f of negative 2 is the opposite of f of 2. I don't get the same thing as I did in an even function. I get the opposite values. That's my indication I have an odd function. So I would say don't be any more concerned about it than this. When I put a number and its opposite in the function, do I get the same thing? Even function. When I put a number and its opposite in a function, do I get opposites? Odd function. That's the concept you need to be familiar with. All right, let's talk about one more concept and then we will start looking at some problems. And here's the concept about a decreasing, constant, or increasing function. Decreasing, constant, or increasing function. This guy is obviously a piecewise function, isn't it? Part of it does this, part of it does that, part of it does this. It's a piecewise function like we looked at in 4.3. Notice, moving left to right, always considering moving left to right, just like you read a sentence. As I move left to right, this part of the graph is decreasing, right? It's going downhill. Again, when I start here, at this part of the graph, the function is constant. It's not going up or down. And this part of the graph, obviously, as I move left to right, is increasing. So this is a decreasing part of the function. This is a constant part of the function. This is an increasing part of the function. All right, here's what Hawks is going to ask you to do. It's going to say, which part of the function is decreasing? And then it's going to say, use interval notation. You remember interval notation, stuff that starts with parentheses or brackets? Well, let's look at the part of the function that is decreasing. That's this part, see the arrow here? It's this part all the way from negative infinity to right here. And what is right here? Let's see. 1, 2, 3, 4, 5. This is negative 5. Let's go ahead and look at this guy. 1, 2, 3, 4, 5, 6. This is positive 6. So and I look at the x-axis to come up with my interval notation. The x-axis. From negative infinity all the way to negative 5. The function is decreasing. It's constant from negative 5 to positive 6. And it is increasing from 6 to infinity. 6 to infinity. Please notice a particular thing here. I'm using parentheses on each of these. Well, which part does the -5 go with? Does it go with this or with that? Is it with the constant part, or it's neither? -5 is a turning point where it stops decreasing and starts being constant. Since it is a turning point, I don't include it in either of these two intervals. Likewise with 6. Is 6 part of the constant function or is it part of the increase? Neither one. It's a turning point. So I use parentheses at 6 to say it's not part of either the constant or the increasing segment of this particular function. So keep that in mind. Don't use brackets here. You're going to be using parentheses. If you got a turning point, it's not in either of the two sections. It is simply a turning point and is not included in either of the sections. All right, let's look at some of your Hawks problems. It says determine if the following function is even, odd, or I guess it could be neither one. So I have u of x is -4 times the cube root of x. So here's what I'm going to do. I'm going to pick a number and its opposite. May I make a suggestion? Pick something that comes out nice and even when I take the cube root of it. 8, for instance, has a wonderful cube root. Cube root of 8 is 2. Cube root of -8 is -2. So let's find u of 8. See what that is. It's -4 times the cube root of 8. It's -4 times 2. That's -8. Now let's try u of -8. Now remember, if I get the same thing, it's going to be even. If I get opposites, it's going to be odd. -4 times the cube root of -8. Cube root of -8, your calculator will tell you this, is -2. Looky there. I get opposites. Therefore, it is an odd function. Well, that was easy. All right, let's try this one. Determine if the following equation has x-axis symmetry, y-axis symmetry, origin symmetry, or none of these. Now, I did not mention this. I think I might have mentioned it in the notes. Let me see if I did. No, I did not. X-axis symmetry, if you have an even function, you have x-axis, what's called x-axis symmetry. If you have an odd function, you have what's called origin symmetry. And you're not going to get any y-axis symmetry, and I'll show you why. Y-axis symmetry means you have the same thing on both sides of the y-axis. Hang on a second. Mistake here. This is y-axis symmetry. You're not going to get any of this x-axis symmetry. And here's why. If I have a parabola, you could say this guy has y-axis symmetry. The y-axis divides it into perfect halves. This is my y-axis. The y-axis divides it into perfect halves. Y-axis symmetry. If I have the absolute value function, hey, y-axis symmetry, perfect halves, divides it right in half. Here's why you're not going to have x-axis symmetry. If I had something that had x-axis symmetry, something that the x-axis divided into perfect halves, what do you notice about this guy? It's not even a function. If it has x-axis symmetry, it does not pass the vertical line test, does it? So we will not be looking at any functions that have x-axis symmetry. That would not be a function. So the guys I'm going to be looking at are either even, that have y-axis symmetry, or they're odd, something that has what's called origin symmetry. I can do this a couple of ways. I can simply graph this guy. This is the negative of the absolute value function. Here's the absolute value function. Now, if I put a negative in front of this guy, if I put a negative in front of a function, it flips it over the x-axis. So putting a negative in front of this guy, here's my new function. Just mirror image over the x-axis. So here's my new function. Here is this guy. Question. Does it have, is it an even function? I know it is because it has y-axis symmetry. The y-axis divides it perfectly in half. This guy has y-axis symmetry. Obviously, what else I could have done to see if it has y-axis symmetry is put in 2 and -2, two numbers that are opposites, and I will get the same thing. So I will have here an even function. Even functions have y-axis symmetry. So sketch it if you can. See if the y-axis divides it into perfect halves. It does. Y-axis symmetry. All right, find the open intervals where the following function is increasing, decreasing, or constant. Express your answer in interval notation. All right, one thing I couldn't do here when I was recreating these problems from Hawks for you is I couldn't copy the graphs. So I will just show you. This is r of x equal -2. Another way to say that is y equals -2, right? So whatever the x is, the y is going to be 7, -2, 10, -2, 2, -2. Here's my function, y equals, or r of x equals -2. Hey, it's a horizontal line. I should know it's a horizontal line because the equation only has y's in it, right? Horizontal line. All right, is there any increasing part? No. Any decreasing part? It's only constant. It just constantly stays the same, -2. So the whole thing is constant, from -infinity to +infinity. And that's the interval notation I use to say the whole number line, from -infinity all the way to +infinity. That's what they're looking for, the interval notation. All right. It says find the open intervals where the following function is increasing, decreasing, or constant. Express your answer in interval notation. All right, once again, I couldn't duplicate the graph, so let me just show you. And we can use this as an exercise for transformation as well. Now check this guy out. This is the basic function that this guy is based on is t of x equal the basic function would be this, t of x equal x to the 4th. If you remember what x to the 4th looks like, it's just a skinnier parabola. Got this handy? Keep this thing handy. Just a skinnier parabola. So I can use my vertex form here to find out where the new vertex of this parabola is going to be. It's going to be at -3, +2. But hang on a second. I have what's called a reflection here. So let's evaluate this guy in light of the order in which I'm supposed to evaluate. Remember this? First of all, is there a horizontal shift? Yes, look at there. Horizontal shift. It's a -3 inside the operation. That means I move it 3 units to the right. It's the opposite of what you'd think. I don't go negative with a negative number. I go to the right. So horizontal, right, 3. And what you're going to be doing on your Hawks is you're going to be putting, yes, there's a horizontal shift to the right, and it's going to ask you how many units, and it's going to move the thing 3 units to the right. So the parabola is now moved 3 units to the right. It'll simply move it. All right, any compressing, any numbers besides 1 multiplied by the thing? No, there's no compression or stretching, so I don't have to worry about that. Next, is there a reflection? Yes, there is. Look here. The negative inside is not being made x, not being made negative. The x inside stays the same. The whole thing, the whole function is being made negative. Since the negative is on the outside, it flips it across the x-axis. So that's what this guy does. There is a reflection. And you choose either across the x-axis or the y-axis. This is an x-axis reflection. And so it'll flip the graph upside down. Finally, is there a vertical shift? Yes, there is. Up 2. And so the whole graph goes up 2. So here's my final look at what it's going to look like. It says find the open intervals where the following function is increasing and where it's decreasing. Obviously there's no constant part, so I don't have to worry about any constant part. So I'm going to choose increasing, and it is from, on the x-axis, from -infinity all the way to 1, 2, 3, all the way to +3. Remember, I use parentheses here. So it's increasing on the x-axis from -infinity to +3, and it starts to decrease at 3 all the way to the right, all the way to infinity. So that's what they're looking for the interval notation. All right. Consider the following function. Now that should look a little strange to you. Namely because it should be in the form y equals. If it is in function form, we should solve this guy for y. So let's note that. Solve for y. So y squared equals -x plus 3. Now I'm putting the x first instead of going 3 minus x. You'll see why in a second. All right, I need square root of this, square root of that. So I get y equals the square root of -x plus 3. First thing it says, determine the more basic function. And what they mean by the more basic function is which one of these guys is this a transformation of? Well, it's pretty obvious. Y equal the square root, right? So the more basic function is y equals the square root of x. That's the thing that's been transformed. All right, secondly, it's going to ask you, it's going to have a bunch of graphs, and it's going to say identify the shape of y equals the square root of x. And you're going to find that guy. It's going to look like that, right? You're going to pick the graph that looks like, oh, there it is, square root of x. That's why you need to have this guy handy. It's because you're going to need to make reference to it as you go along. All right, let's look at the next one. It says, consider the following function. Wow, lots of stuff has been done to this guy, huh? Look at there, a horizontal shift, a vertical shift, a stretching, because that's bigger than 3, and also negative, it's been reflected over the x-axis. But I don't need to worry about that. Here's what I need to answer. Graph it by indicating the more basic function. So find what's the more basic function that this guy represents. Can you tell? It's simply y equals, or f of x equals the square root of x again. So the more basic function is the square root of x. So we start with this guy, and we're going to start doing some stuff to it. And it's going to ask you all the questions. First of all, has there been a horizontal shift? You're going to say yes. You're going to look right there and say to the left. It's going to say how many units, and you're going to say 5. And it's going to move the whole graph to the left 5. All right, next thing it's going to ask is, hey, any stretching or compressing? And you're going to say, yes, there's been some stretching. See that number? It's bigger than 1, so there's some stretching. And we're going to check stretching. It's going to say how much, and you're going to say 3. And it's going to stretch the thing. The Hawk's problem will actually stretch it for you. Thirdly, you're going to ask, hey, has there been any reflection? There's no negative inside the square root, so there's no reflection over the y-axis, but notice there's a negative out front, so that means a reflection across the x-axis. So I have an x-axis reflection, and it will flip the thing across the x-axis. Finally, it's going to ask any vertical shift. And you're going to see that there's a number at the end, and you're going to go, yep, there's a vertical shift, and it's exactly what you would think, up 5. And as you answer these questions, the Hawk's diagram will be transforming. It will be reshaping your basic function into the new expression. So what happened, then it says determine the domain and range. In order to do that, we're going to have a picture of it. So let's get a picture of this guy. Here's what it looked like to start with. We moved it to the left 5 units. 1, 2, 3, 4, 5. Just move the whole thing to the left 5 units. That's what this did. We stretched it. Okay, that's going to move it. It's not going to change the place. It's just going to make it bigger like that. That's what the stretching does. It reflects it over the x-axis. Flip it over the x-axis. That's what it looks like now. Vertical, up 5. It's going to move the whole thing up 5. So my starting point here is now at 1, 2, 3, 4, -5, +5. So the same picture except starting here. So here's my final look to what this guy looks like. And the important thing to remember is this is the point, -5. Starts here, goes forever in that direction. All right, it says determine the domain and range of this function. When it says the original function, it means, it's kind of confusing, it means this guy right here. Now, if I want to look at a graph and find the domain, all I have to do is find the width of the graph along the x-axis. How wide is the thing? That tells me what x values are used. Well, notice there's nothing on this side, right? So it starts at -5 and keeps going infinitely to the right. That's the width of this graph, because this thing keeps going. So the domain, it starts at -5. There is a point at -5, so I'm going to use -5 with a bracket, because there is a point at -5, and it keeps going to infinity. That's the domain. And they wanted an interval notation. That's what this is, interval notation. So again, the domain is the width of the graph. It's from here all the way to the right. The range, you might guess, is the height. And that is, of course, along the y-axis, measured by the y-axis. So if I find the height of this graph, hey, it doesn't go any higher than this, does it? So it's from +5 all the way down. But we do it from the bottom up. We do from negative to, smaller number to larger number. So it's from -infinity all the way to +5. And is +5 part of it? Yeah, there's a point there. So once again, I'm going to use brackets at 5. So the width is from -5 all the way to the right, -5 to infinity. The height is from -infinity, because this thing's going to keep going down. It's from -infinity all the way to +5. Nice little concept to keep in mind if you have the picture of the graph available. All right. Find the open intervals where the following function is increasing, decreasing, or constant. This is redo. Y = 5, that's just a horizontal line, right? That's y = 5. Do I have any increasing parts? I don't. Do I have any decreasing parts? I don't. It's constant from -infinity to +infinity. Interval notation. So that was easy. Anytime you have a horizontal line, it's obviously constant, and it's constant from -infinity to +infinity. All right, find the open intervals where the following function is increasing, decreasing, or constant. Express your answer in interval notation. Obviously, I couldn't draw the graph, so we're going to have to come up with it. Let's come up with a graph using our transformations. Now, first of all, check this out. The more basic function is simply the parabola, f of x = x². That's what's being transformed to get to this guy. So there it starts with. First thing I ask, is there a horizontal shift? Yep, there sure is, right there. And +3 moves it to the left 3. 1, 2, 3. So it now looks like this. Second thing I ask is, any stretching or compressing? Any number in front of the function other than 1? No, no stretching or compressing. Thirdly, any reflections? Is x being made negative inside the square? No. Is the whole function being made negative? Yes. There is a reflection, and that's an x-axis reflection, which means it's going to flip the whole thing across the x-axis. So it now looks like this. Finally, is there a vertical shift? That's a number at the end. Yes, there is, and it's exactly what you'd think. Plus 3, up 3. So I take this graph, move it up 3, and draw it again. And here's the final verdict. And this point is important. It's -3. So once I have the picture sketched, I can find the intervals. Is there any increasing interval? Yeah. This guy's increasing right here. And so from all the way to the left, from -infinity all the way to -3, it's increasing. Remember, I look at the x-axis to see where it's increasing. From -infinity all the way to -3, it's increasing. Remember, parentheses, because this point is not on either the increasing or the decreasing interval. It is simply a turning point. Decreasing, yet decreases starting at -3 all the way to the right. This whole part, all the way to the right. So those are the intervals where it's increasing and decreasing in interval notation. Consider the following function. Notice it's something cubed. Graph the original function by indicating how the more basic function has been shifted, reflected, stretched, or compressed. So let's think about what the original function was. It was f of x equal x cubed. It looked like this. What are we going to have to do? Do the domain and the range. So we're actually going to have to find out what this guy looks like. Here's the original picture of it. All right, first question. Was there a horizontal shift? That's something that's added or subtracted inside the parentheses. Yes, there was, and it is 7 to the left. So it moves this whole guy 1, 2, 3, 4, 5, 6, 7 to the left, and it looks like that. And that's it. That's the only transformation that was done to it. So that was pretty easy. Graph the original function, indicating there it is. So here's the new function. Now the question is, determine the domain and range of the original function. Express your answer in interval notation. Domain is the width of the graph. Now, this may not look like it. You may look like, hey, this guy's just going to finally go straight down, this guy's going to finally go straight up, but it doesn't. They spread out infinitely in both directions. This graph actually spreads out as far to the left or right as you want. So the domain, the width of the thing, is actually from -infinity to infinity. The range, the height of the thing, that's easier to determine with this picture. It obviously goes from as far down as you want to go to as far up as you want to go. -infinity to +infinity for both these guys. So there it is in interval notation. This guy, just one transformation, a shift of 7 to the left. Lots of problems, huh? All right. Find the open intervals where the following function is increasing, decreasing, or constant. Express your answer in interval notation. So we're going to need to sketch this guy. And I have no more questions to answer. No part 2 of this, so I might as well do the whole thing here. Here's the original. It's an absolute value. Find your basic functions. Not there, not there. There it is. Absolute value. It's an upward turning V. So here's what it started off looking like. First of all, horizontal shift. Yeah, looky there. It is to the right. It's opposite of what you'd think. How many units? 4. So this transformation moves the whole thing 1, 2, 3, 4 to the right. So my graph now looks like this. All right, next question is any stretching or compressing? Yeah, look here. There is a 3. There is a stretching because this number is greater than 1, and it's going to say by how much, and you're going to say by 3. Remember what this does. It thins it out. So here's the function before I multiply by 3. Here's my final function. It thins it out. So that's what the thing finally looks like after we moved it 4 units to the right and stretched it. Now I don't have to worry exactly about how it stretches it. I just need to sketch the thing. Now, find the intervals where it is increasing. Here it's increasing. Decreasing. Here's it's decreasing. Nothing constant here, so I don't have to worry about that. So let's do the decreasing first. Remember, it's along the x-axis. So from negative infinity all the way to negative infinity all the way to 4, it is decreasing. Again, 4 is not part of either one of these intervals, so I leave it with parentheses. And is increasing from 4 all the way to the right. We say 4 to infinity. There it is in interval notation. All right. Whoa. Consider the following function. Wow, look at this guy. A lot of stuff has been done to it. Notice that the squared part is in the denominator. So as I look at my basic functions, look at this. 1 over x squared. This is the basic function that's being transformed by this guy right here. The good news is we don't have to sketch this. All we have to do is observe that this is that being transformed. So it says, what is the more basic function that has been transformed? It's f of x equal 1 over x squared. Hey, that was easy. Looked hard, but it's easy. It's just 1 over x squared transformed. All right, identify the shape. And what Hawks is going to do for you is going to put a whole bunch of different function graphs up there, and you're going to have to pick one that looks like this. So you're going to pick that, and away you go. That looked hard? Wasn't. All right, last 2 here. Here we go. Consider the following function. There it is. 3 minus x cubed. It says determine the more basic function. Notice this is a cubed. So I'm going to find something with an x. There it is, an x cubed. And I'm going to say it is f of x equals x cubed. Notice I didn't even have to worry about what's being done to it. Just identify the basic graph that is being transformed. There it is. Secondly, what's the shape of the more basic function? There it is. Have this guy handy? That's no problem. There it is. Yeah. No big deal. All right, last one. Determine if the following equation, by the way, it says 13 out of 14. I skipped one of them because it was basically the same exact question with a few different numbers as another. So determine if the following equation has x-axis symmetry, y-axis symmetry, origin symmetry, or none of these. All right, here's what we might want to do. This looks familiar, right? It's not solved for y. Let's solve it for y. I want to get y, not y squared, so square root of both sides. And I get y is the square root of negative x plus 3. All right, let's do two numbers. A number and its opposite. If I get the same, it's odd. I'm sorry, it's even. If I get opposite, it's an odd function. Even functions have y-axis symmetry. Odd functions have origin symmetry. All right, let's see what we get here. Let's try, let's say 2 and negative 2. Well, let me go in that gets, yeah, that'll work. So, let's call it f of x. F of 2 is going to be the square root of negative 2 plus 3. That equals the square root of 1. That equals 1. Now let's do f of negative 2. That's going to be the square root of the negative of my number plus 3. That's the square root of 2 plus 3. That's the square root of 5. All right, I didn't get opposites. I didn't get the same. I got none of these. So this guy has no symmetry because it is not even, it is not odd. If I'd gotten 1 and negative 1, it'd be odd. If I'd gotten 1 and 1, it'd been even. So none of these. All right, good luck to you with working your problems on Hawks.